next thing we're going to be doing is applying flux to the joints to get ready for our first brazing session. And some of the items will be brazed with silver, some of the items will be brazed with brass, fillet brazed with brass, and you need to use distinctly different types of flux for the two applications. I like to use, actually I only use a water-soluble flux when doing any brass brazing. And there are three of them that I like to recommend. One is Allstate number 11, which is kind of gray in color, and it's a paste flux. You brush it on, you can soak it off later. Another one, this is the one that I've used quite a bit over the years. This particular one's made by Harris, and this is a Welco number 17 water-soluble flux. And it kind of looks like pistachio ice cream. It's greenish in color, and it actually does look like pistachio pudding or something. Then there's this one that's available from Henry James, GFM Type B Paste Bronze Brazing Flux, and this stuff is blue in color. All three of those are water soluble. I do not recommend anything that is not water soluble, because when it comes to removing that old-fashioned type flux, it's just going to be a mess, just a mess. You'll put peen marks in your work trying to chip it away. Then for silver brazing, I've been using Stay Silv white brazing flux from Harris for years and years and years. There are several companies that make white brazing flux for silver brazing. It's water soluble. It soaks off in hot water, soaks off in cold water, but it takes a little longer. But several companies make an equivalent product. I've never really liked using the the black flux. That's also a silver brazing flux. It's supposed to be for stainless. I really don't like using it. I've not been happy with it over the years. If you're going to be building a lot of frames, this should be enough to build, maybe 3 or 4 frames. Even if you're doing all your lugs with silver, that's probably enough to do about 3 or 4 frames right there. It's a 1-pound jar. If you're not going to be brazing very often, they do sell a little tiny one, little 4-ounce jar, which would probably be about enough to get you through 1 lug frame. Another type of flux that's really popular is the gas fluxer. The people who are doing limited production runs or more, full-blown factory runs, frequently use the gas fluxer. The gas fluxer actually puts the flux right into your lines in your torch, and the flux is actually emptied right onto the joint as you're working. Some of the pros just really swear by a gas fluxer. So if you've got the extra bucks, you can contact Henry James at www.henryjames.com and ask about their gas fluxing equipment. And they have all the equipment and all the supplies you need for gas fluxing. So let's go ahead and prep our joints for our first brazing session.
The nice thing about using water-soluble flux is if your flux does dry out, you can add water to it and stir it up and rejuvenate it. Here we're just getting a nice thick pudding-like consistency that'll stick on the tubes when it's brushed on. We're going to flux the seat tube. The seat tube is upside down right now, and we're going to balance the bottom bracket shell on it. We're fluxing both of the mating pieces, and we're going to just rest that bottom bracket shell right on the seat tube. Again, this assembly is upside down. And then we're going to take a ruler, and we're going to get that bottom bracket shell so it's sitting right center on that seat tube. And that's all the fixturing we're going to use for this particular assembly.
We're going to be starting our first brazing session pretty soon. Our fluxing is all done, and our pieces are all fluxed up and set in place and ready to start brazing. A few things about brazing. Number one, for our brass fillet brazed joints, we're going to be using a 3/32 diameter brass rod, and this is just the bulk rod that you buy at your local welding store. It's nothing special. If you want to go the extra money, you can buy nickel silver, which has excellent machining characteristics, and doesn't gum up your files and power tools as much. However, nickel silver, some people are allergic to nickel. I'm one of them, and I break out in an awful rash if I'm exposed to nickel dust. So this is why I use brass. For our silver brazed joints, we'll be doing some joints with silver. I'm using a 56% 16th inch. This is 56% silver, 16th inch diameter, and it's cadmium free. I don't recommend using cadmium containing silver. Cadmium is a heavy metal that can get lodged in your lungs, and it can cause a condition called pulmonary edema, which is a fluid release in the lungs. It could eventually end up in death due to overexposure. Definitely end up in discomfort and lung damage. So I would stay away from anything containing cadmium. Always ask for, one company calls it safety silv. Always ask for the stuff without cadmium, 56%. Also, before we get going, you need to consider protecting your eyes. You can either use a pair of tinted glasses, tinted goggles, or I've changed recently to a tinted face shield so that I can have my reading glasses on underneath because of my eyesight. I'm having problems with nearsighted or farsightedness in my elderly years here, so I like the face shield. The tints that the American Welding Society recommends, that'd be the AWS, they recommend a number 3 tint for silver brazing and a number 5 tint for brass brazing. You can go to their website, I believe it's www.aws.com, and you can find the recommendations there for different tints. Let's talk a little bit about lighting your torch. Never use a match. Never use an open flame to light your torch. Always use a striker. You can use, this particular striker is a flint type striker. This one, I believe they call it piezoelectric. You crank it and you see this funny little spark being generated each time you crank this thing. Those are a couple of really nice strikers. Some places, some large operations will have a pilot flame going where you just swing your torch over to the pilot and light your torch that way. But these work fine for the small shop. Never light your torch with a match. And I think the reason that you need to steer clear of using a match is that after you're done with the match, what do you do with it? Throw it on the floor? What do you have on your floor? Grease, oil, and you've got dark tinted eyewear on, and you throw a match on your floor, you can't see what's going on over there after you throw the match down there. So never use a match, never use something that you're going to discard and possibly cause a fire hazard somewhere. This video is not meant to be an instructional video for oxyacetylene torches. I sincerely recommend that if you do not have any experience with oxyacetylene torches, that you stop the videotape right now, go get yourself enrolled in a vocational ed evening course on using the oxyacetylene torch, and then come back to this point on the tape after you've completed your class. For those of you who do have some experience, I'm just going to cover some quick safety items before we light up the torch. Number one, never, ever, ever, ever run your acetylene pressure at above 15 psi. Acetylene becomes highly reactive, highly unstable above 15 psi. If you run it above 15 psi, if you just dropped a hammer on the hose, that would be enough of a concussion to ignite the acetylene inside the hose. If you drove over the hose with a forklift and you had over 15 pounds, that could ignite the acetylene. It's so unstable. I run my pressures always at 5 and 5. 5 pounds of acetylene, 5 pounds of oxygen. That takes care of everything that I do. Whenever you're transporting tanks, always have the metal caps on them. Got an example here. Always have the metal cap on the tank whenever you're exchanging your tanks. Avoid the possibility of breaking that valve and suddenly releasing a huge amount of pressure, which could actually result in an explosion. Always use the caps. Don't forget that all hoses, all nuts, every fitting leading to the acetylene tank has a left-hand thread, and you can see it all the way up to here. The nuts have little notches around them, which indicates an acetylene line and a left-hand thread. And also the hose is red. All oxygen fittings, all oxygen nuts, everything going to the oxygen tank will have right-hand threads and the green hose. So it's really pretty hard to get them, turned around the other way. Plus, at the tank, there's a male on one tank and a female on the other tank. So there's just no way that you can invert them. Don't ever change those around. Don't ever splice a hose and change the left and the right around just because you think it might work better that way. Don't ever do that. In fact, don't ever splice a hose. If you're tempted to splice a hose, you look, your hose is worn and cracked and looks like it's going to break, throw it away. Do not splice it. Whenever you're lighting your flame, always light your acetylene first. Always turn your acetylene off first. If there's an emergency, if you're having a flame emergency, a fire emergency of some sort, if you turn off your acetylene right away, the emergency should be over because the flame will go out. If you turn your oxygen off first, you will still have a flame. So always acetylene on first, acetylene off first. Okay, we're gonna be using two different tips for our different applications. I'm using a tip with a 35 thousandths orifice. Different companies have different numbering systems, so I find it easier just to tell you what size the orifice is here. A 35 thousandths orifice in this tip, I use that for silver brazing, and we're going to turn on the acetylene first, and we're going to give it a little bit of oxygen. We're going to be using a carburizing flame, and I'm going to bring it up kind of close to my microphone, and you can see that you can barely hear it. I don't even know if it's coming through on the microphone. The tip is nice and long. There's a primary cone in the center, a little short, bright cone in the center. Then there's a longer secondary cone that goes out about 1.5 inches, about 1.25 inches to 1.5 inches length on that secondary cone. And that's what we want to use for silver brazing. It's called a carburizing flame. Let's turn the acetylene off first, and then the oxygen. We're going to remove this tip, and we're going to put on the tip I like to use for brass brazing, which has a 50 thousandths orifice, slightly larger. And let's light this again. Acetylene first, give it some oxygen, clean up your flame, and I use what's called a neutral flame. That long secondary cone, I pull it back in until the secondary cone and the primary cone are the same size. This is called a neutral flame, and this is a good flame to use for welding, gas welding, and for using with brass brazing. I'm going to bring this up kind of close to the microphone. You can hear it. You can probably hear this. I like to have quite a bit more force in my brass brazing flame for fillet brazing, and it's going to sound something like this. That's a pretty powerful flame right there. So, with our torch all set, and our eyewear in place, and our brass in our hand, let's go ahead and start our brazing.
All right, here we have our subassembly sitting right on top of the seat tube, and we're just going to do a quick tack on the back side here, right at the peak of the miter. It's kind of tricky to get this all to the right temperature. You want to avoid pointing directly at the tubing because the tubing is pretty thin. You can point your flame a little bit more directly at the bottom bracket shell because it is thicker. Go to the other side here, and we'll put another tack on. And again, I'm pointing toward the shell more than the tube because the shell is thicker. As you're heating up, this will get red. It'll probably get to a dull cherry red, and then it'll get to a point where it kind of gets glossy. When the steel gets kind of glossy, that's the point at which you can add your brass. Now I've turned this right side up, and at this point I had 2 tacks. I'm going to put 2 additional tacks. I had 1 tack at the back, 1 tack at the front. Now I'm going to do a tack on the left and a tack on the right. And again, I'm avoiding pointing toward the tube. You can point more directly at the bottom bracket shell. Now we're going to twist this a little bit, and we're going to do what I call tinning. And the tinning is basically creating a micro fillet or a very tiny seam along the joint. And basically what I'm doing here is I'm kind of reheating those tacks and kind of pushing them around the corner, and just making that very, very tiny fillet all the way around. And then when I get to the side here, I'll flip that shell over, and we'll do the other side. There we go. And now I'm going to tin the other side. After I get done tinning, it will be attached all the way around. I tend to blow my excess heat off into the midair rather than pointing directly at the metal. Kind of point your excess heat out into the air. Now I'm going to tilt this 90 degrees and kind of drop it down a little bit so I can drop some brass into that little right angle area right in there, and I'm going to build a little web between the bottom bracket shell and the seat tube, building up a little web. And this is so that we get strength from side to side. I'm not going to build up very much material at the front and the back of the shell because we still have other tubes coming in there later. Now I'm going to build up another web on this side. And you notice I use kind of a dabbing motion, and notice that my flame and the end of my brass rod are very, very close to each other. They're probably within about 5 or 6 millimeters of each other. That way the brass rod is always close to the right temperature to be working. If you get too far away from each other, the brass rod cools down too much, and then it takes too long to heat up the end of that brass rod. So here we are, we're kind of doing a dabbing motion. Notice that when my torch goes up, the brass goes up. When my torch goes down, the brass goes down. They stay right by each other. And I'm doing a little dabbing motion here, and I'm filling up, and I'm making a little bit of a web connecting the 2 tubes. Kind of a radius. I'm building a radius right there. There, you can see that radius. And then I'm going to put just another, a little bit of a web between where the chainstays are. So I'm going to put, build up just a little bit between there. Now we're going to get ready to flux the lower head lug joint. There I'm pointing at my mark for my intercept. This large tube that's going inside there is kind of a snug fit, but not a really hard fit. And that's it's basically a heat sink. It keeps your head tube from going ovalized on you while you're brazing. And it also makes a nice counterbalance. I'm moving it in and out, and I'm getting it just to the right length so it counterbalances the head tube, and the head tube will sit there for us without any jigging. That's it. There's no jigging for this joint either. I'm lining up that intercept right now, getting that intercept lined up with the bottom of the down tube. And now I'm going to flux that joint. Again, here we're going to apply generous amounts of flux. You can't add flux after the joint is hot. You have to add all your flux before you start heating. Adding cold, wet flux to a hot joint can have a bad effect on the internal characteristics of the steel. Now we're getting a neutral flame there with our 050 orifice. Now here again, the tube with the heat sink in there acts as a much more massive piece. So I tend to favor the head tube because of that heat sink inside there, and I avoid pointing too directly at the down tube. I'm tacking on the sides, one tack on the left, one tack on the right, and after those 2 points are tacked, the joint will hold together, and I can tilt this down so that the joint is down rather than up in the air. After my tacks, I check on the drawing to see how the angle of the head tube and down tube check out. I'm putting this on the V-block build-up, and I'm going to take a machinist square, and I'm going to use that machinist square to line up 3 points above the drawing. I'm still working on my build-ups here. The weight of that heat sink is making this want to kind of twist and tilt. So I have to put a little build-up underneath the heat sink. Now everything's sitting nice and flat. Get these out of the way here. There's my machinist square. Line up a line, line up a point on the line, check it again, get them lined up, a third point, check the third point on the line, shuffle it around a little bit, check the points again, 1, 2, and 3, and then check the fourth. How does the fourth look? Does it have to go forward? Does it have to come backward? Well, the joint had to go backward, and so what we need to do is we need to add a little bit of a tack on the back side, on the top side of the down tube. When that little tack cools, it'll pull the head tube back a little bit. I don't want to build up any complete part of this joint yet. I'm just playing around with the tacks at this point. And once we get this tacked, then we're going to go back over to the table and we'll check it again to see exactly what kind of effect this third tack has on this joint. Careful heat control like this can do wonders for reducing the amount of cold setting you'll have to do later. Again, I can point almost directly at the head tube because of that large heat sink that's inside there. That heat sink absorbs a lot of heat, but I don't want to point directly at the down tube because the down tube is only about 1 millimeter thick at the most. And that down tube can't take a lot of heat. You could burn a hole through that down tube in very short order. Checking the joint again to see how it reacted after putting that third tack in place. Line up 3 points and check the fourth. It may have pulled it back too much. If it pulled it back too much, we can do a little bit of cold setting. Put it back on the table. Check 1, 2 points. Check the third. Again, 1, 2, 3. 1, 2, 3, and then check the fourth. Where did it go? Is it too far forward, too far backward? I guess we're going to do just a little tiny bit of cold setting there. And we're going to get this joint so that it matches that drawing just right. This joint is one of the most critical joints in the bike. If you get off on this joint, it gets worse as you go further away from the joint. It's sort of like making the corner of a house out of square. By the time you get to the opposite corner of the house, things are really messed up. So same thing with a bicycle. This very important joint, if you get too far out of square or too far off the angle, by the time you get to the other end of the bike, things are really a mess. Check again the 3 points and the 4th. All right, the angle matches the drawing quite well at this point. And so what we're going to do now is we're going to pretty much finish the sides of the joint, the left-hand side and the right-hand side of the joint. This will strengthen the joint without having any kind of an effect on the angle of the joint. So here we are, we're doing a lot of filling on the side. Again, it's kind of a dabbing motion with the torch and the brass rod. One thing you'll notice when you're brazing is that there are some factors that tend to affect where your brass is going to go. Probably the most influential factor is gravity. You notice that I keep all of my work directly on top. Keep that nice and flat. Keep the work directly on top. And gravity will let you make a pool directly on top of your work. If you try to work over the edge and get away from that topmost part of your work, your puddle is going to drop off onto the floor. The next thing that has an effect on your travel of your brass is the heat. The brass will follow the heat. So if you heat up in front of it, the brass will go that way. If you heat up behind it, the brass will follow the flame the other way. Third of all is the force of the flame. You've got 5 pounds of pressure coming out the end of that tip. And 5 pounds of pressure on that little tiny puddle can blow your brass one way and then the other. So using those 3 factors, you can control quite carefully and quite exactly where your brass is going to go. Now we have these 2 side joints, 2 sides of the joint pretty well built up. At this point, I'm kind of working my way up near the top of the joint, but I'm not going to build my fillet all the way around the top of the joint. This is going to be a kind of a small frame, and if I build that fillet all the way around the top, my top tube isn't going to fit in there. So I'm going to build about 3/4 of the way around the top. I'm going to leave that last quarter undone around the top of the tube. After I get those areas built up, then I can go down inside here and I can build up the acute angle of the joint. The acute angle of the joint has a lot of pulling power. Let's check to see how the angle is looking right now. Again, we're checking 3 points or lining up 3 points and checking the 4th. And we're looking to see exactly what's going on with this joint. Do we need to fortify the sides of the joint more? Do we need to do underneath there to pull the joint back the other direction? By this point, the joint has probably pulled back a little bit at the top of the head tube, so we're going to start adding material up underneath that acute angle on the bottom side of the down tube. And that acute angle has a lot of pulling power. That's why you want to save that area of the joint for last. If you did that acute part of the joint first, it would pull your joint so far out of tolerance that you'd probably have to redo the joint. You need to do that acute angle last. Notice when I'm doing this, I'm blowing my excess heat to the side. I'm kind of blowing my excess heat through that triangular area in that acute angle area. Don't point your torch directly at the down tube. You can point a little bit more directly toward the head tube because of the heat sink. And you've probably also noticed that we flip this angle quite a bit. We flip this joint. Sometimes when I'm doing one of these joints, I flip it 15 to 20 different positions, always trying to keep my work area or my puddle directly on top. And the more you flip it, the more control you have over the angle or over the radius that you're trying to build on these different webs. Also, after I get done building a web, I'm building a web right down inside this angle area here. And after I get done building the web, I'll turn this joint flat, and I'll use that web as a dam to keep my my brass from falling on the floor. Here's a quick splice. Keep from wasting your welding rod. You can splice it together while you're working. And then here we are. We're using that web now as a dam, and we're dropping more brass into that hollow area on the lower side of the joint. And again, trying to keep our work area directly on top. You always want to avoid any white flares. If you see, as you're brazing, if you see a white flare shoot out of the metal, and they're not very big, they're if you see one, it'll probably flare out about 3, 4, 5 millimeters. But if you see a white flare like that, you've badly damaged that tubing. You've burned some trace elements out of that tubing. And so you need to avoid those white flares. If you're getting those flares, you need to adjust your angle of your flame so you're not pointing straight at the tube. You need to flatten out your flame rather than kind of use a brushing motion with the flame rather than a poking motion. Use a brush from the side rather than a poke straight on. Those little flares, when they jump out, they are an indication of some serious changes in the metallurgy of your project. You can see that this joint is getting tilted many times, and the more fine tuning I do on that tilting, the better control I have over that little puddle that's on the direct top of my work. You can see from this angle that plug that's in the head tube is actually a solid plug. It is possible to use a thick wall plug. You could use a plug with a wall thickness of maybe 4, 5, 6 millimeters. Here we are from another angle. It's kind of difficult to explain how the flame has to shoot its excess heat past the tubes, but maybe you can see here every now and then I lift up my torch handle and I shoot my excess flame through that triangular area. That way my excess heat is shooting out into nowhere and it's not going into the frame. And I do that, and by doing that I can avoid getting the tube too hot. Again, I'm tilting this tube many times during the brazing process. At this point, our tubes have had plenty of time to cool, and the flux is like glass now. You can see that I have webs on the sides and a web on the back of the bottom bracket, but there are openings where the down tube and the chainstay will fit in later. Those areas have not been built up. After the bottom bracket has cooled sufficiently, you can soak the flux off in hot water, and it'll get that bottom bracket nice and clean. And at this point, we are going to tap and face the bottom bracket so that we can cold set this joint. It's very important that you put the left-hand tap in the left-hand side, and don't forget to take a look which side is that counter bore or that chamfer or that little machine mark that indicates the left-hand side. And also on your tap, which side of the tap is marked LH. Make sure that you are tapping the left-hand threads on the right-hand side of the bike. If you do it the wrong way, you're going to end up cutting this bottom bracket shell off again and redoing this joint. Use plenty of cutting fluid. These are line taps, so they go, they have a shaft going down through the center of them. I anchored one side, and I'm going to bury this side. If you keep your taps nice and sharp, they're easy to turn. After a while, they start getting dull, and it starts getting to be a lot of work to twist those taps in. If you're experiencing a lot of fatigue in trying to tap these threads, it probably means you need to get your tap sharpened. Anyway, we're going all the way in. We're going to bottom this out. Since we're not cutting new threads, we can just keep on going in the same direction. When we bottom it out, we can back it out again. Again, we're using a cutting oil that contains chlorine and sulfur, which improve the quality of the cut and keep the heat down. I'm not going to take this side out all the way. I'm going to leave it anchored a little bit, and then I'm going to bury this side. A little cutting oil helps keep the cutter cool, cuts down friction, and we're going to bury this side all the way in. Sometimes people insist that you have to go back and forth when you're tapping threads. The benefit of going back and forth when you tap threads is that as you move the cutter back, the oil seeps into the furrow, into the furrow of the thread, and then you advance forward and you have oil down inside there. Then when you back up again, the oil seeps into the furrow and you have fresh oil in there. So that's the benefit of going backward and forward. Okay, we're all the way down in on this one, and we're going to unscrew this. And there's kind of a knack to doing this. I like to get them all the way out until they're nice and loose, and then spin both of them and pull them both out at the same time. That way your threads don't hang up on the outer thread of the bottom bracket shell. See how they popped out both the same angle? Clean your taps off after you're done. You can blow them off, squirt a little WD-40 on them, get them nice and cleaned up and ready for the next time you use them. Don't set your taps close to the edge of the bench. Set them back away from the edge so someone doesn't come by and knock them on the floor. Now clean the chips out of here. And we're going to put the guide sleeves from the Campagnolo bottom bracket facer or Cobra bottom bracket facer. We're going to screw those guide sleeves in. These guide sleeves will give the facing tool a precision bore to locate on as it faces the two sides of the bottom bracket shell. Of course, since one side is left and one side is right-hand thread, they both go in the same direction. The shaft of the facing tool can reduce the amount of chatter that you get when you face the bottom bracket. My favorite bottom bracket facer is either the Campagnolo or the Cobra. They really do a superior job of facing, and it's largely due to the precision sleeves that were just screwed in. Put your assembly on the end there. Screw this adjusting nut on the outer end. Lots of oil. Generous amount of oil. And one thing important about facing tools is you never turn them backwards. Never, ever turn them backwards. If you turn them backwards, you will dull them in a hurry. I don't have a whole lot of pressure set on here. Medium, moderate amount of pressure. Back it off a little bit. Back it off a little more. See how I'm backing off that nut on the left side there? That's so I can take a finishing cut. And we're going to take a look there. You have to go at least 3/4 of the way around. This bottom bracket shell is actually a 69 millimeter that I've liked to use in the past. It allows me to face as much as a millimeter off and still end up with a 68. Okay, we're facing this side. Again, we never turn backwards. Every now and then I give that adjustment nut a little bit of a tweak so I get moderate pressure here. And I like to push on one handle. I found in the past that if I push on both handles, I may get some chatter, but if I push on one handle, I don't tend to get as much chatter. Loosen it up for a finishing cut. Loosen, loosen. There we go. And we should have it clean about 3/4 of the way around. We're going to leave those sleeves inside there, and we're going to go over to the alignment table. This is an alignment table that I made from the bed of a hardened chucker, and it's a beautifully flat piece of dovetail hardened steel. The design I have used to create my plans for fixtures, and if you have a copy of the Paterek manual, there is a set of plans for fixtures in the back of that manual. One of the fixtures that can be built is an alignment table very similar to this one. You can see how I use the seat tube almost like a wrench there. I put the bottom bracket shell on the shaft and use the seat tube to kind of tighten it up. And now I'm taking a universal surface gauge and I'm getting it to scratch down there by the bottom bracket, and I'm getting it to scratch up by the end of the seat tube. We've got a little bit of deflection there, so we're going to stick a cheater bar inside and either raise or lower to get those 2 points the same. Okay, we're going to come up on that. Take the cheater bar out before you take your readings again. The weight of the cheater bar can throw off the readings. Okay, give it a little bit of a tick and use your hearing. Don't use your sight here, use your hearing. Several tries before you get it right. Again, we'll bring out the cheater bar. That cheater bar, by the way, has a miter cut in the bottom where it bottoms out against the bottom bracket shell. And we tweak it a little bit there. And then we'll take our readings again. This is kind of a test and check sort of procedure. Remove your bottom bracket sleeves. You're all done using them. They can go back in the mechanic's tool case now. You don't want to expose them to heat, and you don't want to expose them to any kind of acid cleanup because they are precision tools. So remove them and put them away. Again, here we have some water-soluble flux, so if it dries out on you a little bit, just add a dab of water and stir out the lumps and get it nice and smooth and creamy. Get it to kind of a thick consistency so that it'll kind of cling to the pieces. Right now we're going to do a pre-assembly of the fork. We're not going to actually build the fork at this point. What we need to do is we need to find out exactly what plane the dropouts have to lie in. And to do that, it's easiest to pre-assemble this fork in the jig and tack those dropouts in the jig. You'll notice that these fork blades are different from the ones that we bent earlier. These fork blades are actually straight blades. The straight bladed Unicron fork is probably the easiest fork to build in frame building. We're putting this water-soluble silver brazing flux up inside the tubes, and we're also going to put it on the dropouts. You need to flux both of the mating pieces. If you flux only one piece, the flux gets squeegeed out in one direction and not in the other direction. But if you flux both mating pieces, the flux kind of gets squeegeed in both directions, and you get good coverage for brazing. And we're going to hold everything together in this jig to make sure that those dropouts are not rotated. So let's come back and check this out when it's all set up. Into place now, and there's a toe clip strap holding the blades together so they don't fall on the floor. And then we're taking the universal surface gauge, and we're going to use that, and we're going to check at the top at the curvature of each blade to make sure that they're both sitting the same height so that one blade isn't rotated differently from the other. There's no rake designed into this fork at this point. We're just holding things in place so that we can braze those dropouts in the right plane. So you were probably looking at that and wondering, why isn't there any rake on that fork? Well, there isn't any at this point. Checking one side, then the other. Until you get both sides at the same height. There we go. When we get both sides the same height, we can tack those dropouts. Now here we're using the 56% CAD-free silver, and I'm using a 35 thousandths orifice and a long, gentle carburizing flame. Not nearly the amount of heat here as we were using to do the lugless joints of the bottom bracket shell and the lower head lug, or the lower head joint. This requires a slight preheat. What you want to do is you want to watch your flux. Your flux will start out as a wet paste, and as you warm it up, the paste will dry out and it'll become a dry crust. And then the dry crust will become a liquid form with bubbles in it. And as you heat up more, you watch those bubbles. And when the bubbles in the flux are just about ready to disappear, that's when you can add your silver. Silver does follow the heat of the torch. You can pull that silver uphill if you want to. Notice how I'm pulling flux back up onto the joint. That is a problem with silver brazing flux, that it falls off onto the floor a lot. You lose a lot of flux, so you have to get in the habit of dabbing away and scooping it up and putting it back on the joint, because you can't put wet flux on a heated joint. Putting wet flux on a heated joint will cool the joint much too quickly, because that wet flux is, over 1,000 degrees cooler than the joint when it's at brazing temperature. If you think you need more flux, then gob a little bit about 3 or 4 centimeters away from the joint. Just gob it on there, and then if you need it, it's close to the brazing temperature and you can scoop it onto the joint. There we go. We have 2 good-sized tacks there, and because we did this in the jig, we know that these 2 dropouts are in the correct plane. So at this point, we're going to take these out, and we're going to put them in the vise and finish them off. We have the dropout pointing straight up into the air, and we've got our torch all set to go here. Same flame, carburizing flame, 035 orifice, and a long, gentle, quiet flame. I tend to put more of my heat toward the dropout. The dropout is quite a bit thicker than the fork blade. If I point my heat too much at the fork blade, the silver will literally jump onto the fork blade. If I put more of my heat toward the thicker dropout, and then, kind of work my way toward that little seam, favor the dropout, work toward that little seam, favor the dropout, work toward the seam, then the silver should fall onto the seam. But it does take a lot of heat control here. So it's also a blind hole or a blind joint. You can't see inside there how much you're using to fill this joint. I'm going to say that probably 2.5 inches of silver per dropout will be adequate to hold these plug-in style dropouts in place. And there we go. There we've got our dropout almost completely finished. I turned it around so I can see the other side a little better. And just drop that silver right on that seam, and it'll get literally sucked right inside the joint. You want to make sure that you don't give that dropout any kind of a twist while you're doing this, because if you give it any kind of a twist, all that work we did in the jig will have been for nothing. We're fluxing up the chainstay rear dropout joint. Again, we flux both pieces and assemble them in the vise. I never use jigging for this particular joint. I just use gravity. And then we lean it kind of at an angle, so the dropout, the weight of the dropout is pressing against that outer scallop of the joint. And we do this joint right inside the vise. Same tip, 035 with a carburizing flame, quiet carburizing flame. Here again, you want to favor the dropout because the dropout is quite a bit thicker than the tube. Because it's so much thicker, it will tend to absorb more heat, or it will tend to accommodate more heat. The tube, on the other hand, since it's thinner, can get red. We don't want our material to get red while we're silver brazing. We should be able to work at a temperature at which the tubing, the dropouts, whatever we're working on, stays pretty much gray in color. If you're getting your tubes red, you're getting things too hot. One interesting thing is if you turn out all the lights in the room and do your silver brazing, you will see a very dull red glow, but it'll only be if you have all the lights turned out in the room. Otherwise, you won't see any redness at all. And we're filling here. There are some builders who insist that you can't attach dropouts with silver because you can't fill large gaps with silver. However, you're watching it right now. You can fill plenty big gaps with silver, and we're filling up those holes in the sides, those scallops in the sides of the joint right now. What you do is you kind of rely on very careful heat control and the surface tension of the liquid silver. Here we have to work kind of quickly. If we work too slowly here, that dropout will kind of fall cockeyed all of a sudden. Just the weight of the dropout will make it drop suddenly because it doesn't have anything to press against on the inside face. Again, kind of point down inside there and start feeding that silver. Notice how I brush the flame out of the way rather than pull back and continue to point at the joint. I brush the flame out of the way. When I want to see the joint, I brush, take a look, brush back in again. Blow your excess heat out into midair. There we go. We just filled some large gaps. Very easy to do. And now we'll do the left one. Left one has to be held at a slightly different angle because it doesn't have that even pressure that the right dropout has. The left one tends to want to fall toward the seat stay tab, so we have to put it at a slight angle to get it to sit properly for us. And here again, favor the dropout because it's thicker. Point your flame more toward the dropout, less toward the tube. So while I'm doing this, I'm constantly scooping flux back up onto the joint. It just tends to fall onto the floor all the time. That's one of the real drawbacks of silver brazing, just losing that flux all the time. Again, when the flux gets nice and clear and the bubbles in the flux start to disappear, it's time to add the silver. If you overheat the joint and the flux starts to turn muddy, you don't have much time left. When the flux starts to turn muddy, it will no longer do its job of keeping the joint clean at high temperature. That's the main job of flux. It keeps the joint clean while the heat is being applied. And if you get the joint too hot, if you get things red, the flux will turn to mud. When the flux starts looking like mud, it loses its cleaning abilities, and before long, it will not work at all. Again, scoop up that flux, drop it in.
Quick item to mention, I almost forgot to talk about this, and that is use of respirators. I would really highly recommend that you go out and buy yourself a nice canister type respirator for doing your brazing and silver soldering. The soot and the particulates and even the metal gases that are given off during these processes can be quite damaging to your lungs. Get one with removable canisters so you can unscrew them and replace them on occasion. And on the sides, it'll tell you what the canister is appropriate for, whether it's for chemicals or whether it's for soot or whatever. You can always ask your safety supplier what you should use. There are a number of safety suppliers listed in the resource book, or in the resource section in the back of my book, and a couple that come to mind are Continental Safety, Elvin Safety Supply, Sanderson Safety Supply. Most of these places are listed on the web. Just do a web search for industrial safety equipment, and you should find a whole bunch of different suppliers that can help you choose the right type of respirator for the application for which you want to use it. Now that the first brazing session is finished, you should have some sub-assemblies now. Your head tube is joined to your down tube, your bottom bracket shell is joined to your seat tube, your dropouts are joined to your fork blades and your chain stays, and if you're using a crown on your fork, you'll have a crown and a steering column joined. If not, you won't have that at this point. At any rate, after these items cool, you can soak them in water to soak the flux off. Remember, this is water-soluble flux. Cold water will take about 45 minutes or an hour to soak off. Hot water, the flux should soak off in a matter of minutes. I use, my favorite item to use for soaking flux off of joints is I have a wheelbarrow out in the backyard, and I just fill it with water. It's one of those plastic wheelbarrows that you buy down at Home Depot. Fill it up with water and throw your pieces in there. Remember, very important, don't put hot pieces in cold water to soak the flux off. They must be cool to room temperature. If you put hot pieces in, it will alter the crystalline structure in the steel, and you could severely damage the internal properties of your steel. So now that we've got our pieces fluxed, or now that we have our pieces soaking the flux off, as soon as we pull those out, we can move on and go on to do the front triangle.
Okay, at this point, I'm laying the hockey stick into the V blocks. I call it the hockey stick because it's shaped like a hockey stick, and the hockey stick is made up of the head tube and the down tube. You can see that I'm putting a tubing block at the bottom end of the down tube. I'm holding the hockey stick flat against the table in the V blocks, and I'm using a machinist square to make sure that this tubing block is square with the table. That will make sure that when I clamp this down tube in the milling machine vise and make my cuts, that my cuts will either be in line with the central plane of the bike or perpendicular to that central plane. And that's why I'm using the table to set my my tubing block. Now I'm locating the hockey stick on the drawing, and I'm going to determine where my rough cut is going to be. We'll put a little bit of blue layout dye on the tube. Let's scoot a little piece of plastic under there so we don't get any blue layout dye on our drawing. And the rough cut can just be kind of eyeballed. And we're going to take this over to the bandsaw, and we're going to make a rough cut. The rough cut's going to go roughly through the center of the bottom bracket shell. And that's what I've marked at this point. You can see I'm missing the blue layout die, but the blue layout die is for my final cut. I just have to get that piece of tubing out of the way for my rough cut. Now, the rough cut does not have to be square, because we're going to be using an angle plate as our vertical reference plane. And so I'm going to check 3 points here. Make sure the hockey stick is lined up on the drawing. Takes a few trial errors to get this hockey stick lined up. Once it's lined up, we move that angle plate against the bottom end of the down tube. There it is, the angle plate. And then I have these little stubby rulers, little itty-bitty stubby rulers. And I'm going to measure from the angle plate to the outer diameter of the tube. And then I'm going to transfer that measurement up to the top here. I use that angle plate as my vertical reference. And that right there, that is where the miter is going to be. Now we've come over to the milling machine. I've mounted the down tube in the milling machine vise, and because the down tube, the hockey stick, was held firmly in the V-blocks, and we use that machinist square to tighten down the tubing blocks, we know for a fact that that set of tubing blocks is square with the bike. Now we've got a bottom bracket cutter that's same thickness as the bottom bracket, and we use the piece of paper as a feeler gauge, and we're figuring out our cutter travel here. Radius plus 3/1000 for the paper. And we're going to lock that cross feed, and we're going to come down, we're going to find that mark that we made, the mark we made in the blue layout die with the little short stubby ruler. All right, there we are, right on the mark. Give it some cutting oil, and we'll come right down through. I'm feeding with the knee because the knee is always more positive feed than the quill. And there we are, we've got a nice cut there. And of course, after we make this cut, we're going to have some sharp burrs on it, and so we're going to need to go over and clean up those burrs, and we're going to have to shorten the peaks on the miter so that they don't burn up during brazing. And so we'll flatten those off a little bit right now. Remove the burrs so we don't cut ourselves. Flatten that side off too. Just like we did with the other joints. All right, let's set this in the V-blocks and line it up with the drawing. Use the machinist square to line this up with the drawing. 3 points will get it lined up. Now we've got a bit of a problem with this joint, and that is that that top part of that miter is going to hit the seat tube before the miter bottoms out on the bottom bracket shell. And so what this means is we need to do a compound miter down there to accommodate that. Checking the bottom bracket shell, looks good, right on the edge of the circle there. So we're right at the right length. But now we've got to figure out how to do that compound miter, because that seat tube is interfering. Now there are different ways to do this. Some builders will squish their down tube, and they'll squish their seat tube, and they'll just do a simple miter on both tubes, and because they're squished, they won't touch each other, and they'll be easy to braze. However, some builders, I'm one of them, I like to do a compound miter. I just think it looks a little better, and so I go the extra distance here. Now I'm measuring where that seat tube is going to hit right there. Now we're taking the angle off of the drawing, right down there where the seat tube and the down tube hit the bottom bracket shell. It's an acute angle. Here we're going to transfer that angle to the milling machine. We're getting that angle between the cutter and the down tube, and then we're going to get everything centered up, just like we've done on all the other joints, and we'll cut that compound miter. And here we are. We're all lined up, center on center, and we're starting it up, and we're going to cut that little compound miter. We're just cutting something about the size of my thumbnail out of there, so it doesn't take very long at all to do it, and it's all done. And get that all cleaned up and deburred, and get the burr out of the inside there, and let's take a look. There's our finished compound miter right there. We have the hockey stick and the seat tube bottom bracket assembly above the drawing. It did take a few little fine tunings with the file to get this compound miter to fit together properly, but not a lot. Eventually you get all the pieces right there to come together without any gaps of light in them. And at this point, we're going to flux it up and we're going to tack it on the table. This is going to be a lugless joint, so we're using the Welco number 17 again. Generous amount of flux. Notice that we're using weights to hold the assembly down tight against the table. Notice also that there's a piece of scrap metal underneath our brazing area so that we don't burn our drawing. And we're going to put several tacks in here. I usually do at least 4 tacks at this point. You have to work fairly fast and avoid overheating the tubes. It's difficult to do these tacks from up underneath. There we are. We're all done with the brazing. And we'll lift the large aluminum weights off the frame. Those are the weights that secure the frame to the table. This joint is very delicate at this point, and so when we transfer it to the park stand, we have to carry it very carefully. And what we need to do now is we need to put additional tacks on the joint. Don't reheat any of the tacks on this joint until you get an adequate number of additional tacks in place. If you were to reheat any of these tacks at this point, the joint could fall apart or lose its angle, which would not be good. So at this point, let's go around the joint and turn our 4 tacks into 8 tacks. And after we do that, we can start building the webs that we talked about earlier and start building up the fillets. One thing that we find is that the acute angle between the down tube and the seat tube should be done last. Because the acute angle has a lot of pulling power, we want to do the bottom part of the bottom bracket shell, the part that I'm doing right now. We want to do that first to stabilize the joint. We want to get the left side of the bottom bracket. We want to get a web built in there. We want to get a web built in the right side of the bottom bracket. And we have to get all of that stuff done all the way around the bottom before we start building the acute angle, which will pull the joint way out of tolerance. This again requires a lot of dabbing motion. Notice how the brazing rod and the flame kind of dab in tandem with each other, up, down, up, down, up, down, both of them at the same time. Notice that I continually turn this frame many times to keep my work area directly on top. When you get the bottom end of the joint done, you can start working at the top end. This is kind of a tight area to work in here. You need to be quick about what you're doing in here or you'll overheat your tubes. And this is a long joint to do. This will take the beginner probably 20 to 30 minutes, which is a long time to keep a joint hot. The less time you spend with the joint being hot, the better. It's nice to do this joint in about 10 or 15 minutes, but that takes a lot of experience before you can do it that fast. Notice the number of times I'm tilting this joint continually, just a few degrees at a time, just to keep my work on top. After the bottom bracket joint has had sufficient time to cool, we're going to have to soak the flux off, and then after the flux is completely soaked off, we're going to have to check it on the drawing to see how well it matches the drawing. More than likely, the seat tube has pulled forward and no longer matches the drawing. So there we are. We're doing our cold setting. We're pulling the seat tube back again so that the joint matches the drawing again. Check 3 places on the hockey stick. When you get the hockey stick lined up on the drawing, then check to see if your seat tube lines up on the drawing, and you may have to bend your seat tube forward or backward to get it to match the drawing. have to re-tap the bottom bracket and face it again. Very important, determine which side has the left-hand thread. There should still be that little depression in there or counter bore that indicates the left. Notice that I just marked LH with that Sharpie marker on the bottom bracket shell to match the LH that's marked on the bottom bracket taps. And notice I gave them a couple turns just to anchor both sides. And now I'm going to get my cutting oil, and we're going to add cutting oil, and we're going to bury one side just like we did before, and then we're going to back that side out and bury the other side exactly the way we did before. And here we are. We're going to put our precision sleeves in the bottom bracket, making sure that the right hand thread is on the left hand side of the bike and vice versa. And we're going to run them right down inside, and we're going to use those little keys to bottom them out against each other just like we did before. We don't want to overdo it on the bottom bracket facing, because if you really overdid it, you could go way undersize. I've seen bottom bracket shells that have been tapped as narrow as 66 millimeters, when they should have been a 68. With that extra millimeter that we had when we started out, if we cut carefully, we should end up with very, very close to 68 millimeters. It doesn't hurt to go a little bit undersized, but I don't think 2 millimeters undersize is a good policy. Again, grease the shaft to cut down any chatter that might occur with this tool. Never turn this tool backwards. This is an identical procedure to the one earlier in tapping and facing. And we're going to be using medium to light pressure. Medium pressure to do the initial cut, and a light pressure to finish off with a finishing cut. And we will not be turning these backwards at any point. We'll be leaving the sleeves in because the internal bore of the sleeves fit exactly on the alignment table. The bottom bracket shaft on the alignment table is turned to match these sleeves perfectly. Slip it right on there, put the big nut on, and you can actually use the frame to do the final tightening. You can make yourself an alignment table just like this one. In my book on frame building, there's a 66-page set of plans for fixtures to for anyone who buys the book. They can make their own set of fixtures, alignment table, whatever you see in this video, basically. We're checking for down tube deflection right now. We're taking a reading up near the top, and we're taking a reading down near the bottom bracket. We don't want to take a reading too close to the head tube, because don't forget we squished that down tube a little bit because that miter didn't quite match until we squished it. Take a check, see if you have to bend up or down. Apparently we have to bend down a little bit. Don't overdo it. I've seen people put a ripple in right down there by the bottom bracket shell. We're pretty close because I went by at that time, and now I had to go back up. We're just kind of right between there. We're very close to where we want to be. We're using our ear here, not sight. We're listening for a little ting from the universal surface gauge. Loosen it up a little bit. Swing the seat tube over the bed, and then we're going to double check the seat tube. Again, set it till it just grazes the tube, and again, check it there. And we'll use the cheater bar because we can use the cheater bar. Obviously, we couldn't use the cheater bar in the down tube because there's no way to shove it inside. And we'll just spend a few minutes getting this set so that all 4 points are all right on the money. All right, we're pretty much at some of the final stages here on this front triangle. We've got it set to the drawing, and we have the deflection eliminated from the down tube and the seat tube. And so now we'll put it above the drawing, and we'll put our top tube in place. Now remember to put this top tube right from one end to the other. We don't want to put it in backwards. Actually, if you do put it in backwards, because of the difference in the seat tube diameter and the head tube diameter, putting the tube in backwards will actually push the frame apart 1 to 2 millimeters. So make sure you're putting it in frontward. And use the machinist square to make sure that all the tubes line up with the drawing. And we're going to get this thing ready to tack. We've got it in the park stand now, and we have located where the vent hole has to go into the back of the top tube through the seat tube, and we've punched it, and now we're going to drill it. I don't put as big a vent hole in the seat tube as I put into the head tube, because the seat tube reamer has to go through there, and if the hole is too big, the blades of the seat tube reamer can get kind of hooked on that hole. So I keep this one small, probably about 3/16 of an inch or so. Clean it up after you drill it. And then we'll have to measure for the rough cut for the seat tube length and the head tube length. We've got it on the table again, and we're using the machinist square to get all the tubes lined up just right. And when you get them lined up just right, one thing that happens is the top tube wants to creep when it's in place, and so we're going to put a modified C-clamp on the seat tube to keep that top tube from creeping upward. The front of the top tube is resting against the top of the down tube, so it can't creep downward. But if the bike were bigger, we would have the creeping problem at both ends, and we'd have to use a modified C-clamp at both ends. But the bike is quite a bit smaller, and we're not having that problem at the front. Now there's a mark for our rough cut. Another mark for a rough cut, and we're going to cut those off short. Cuts can be made on the bandsaw, because later we'll go through and run our reaming and facing tool on the head tube, and we'll be cleaning that up. And we have some finishing work to do at the top of the seat tube, so the bandsaw works fine for this. The seat tube and the head tube were cut so that they extend about 20 millimeters above the top of the top tube. That should leave us enough room to build a fillet in those areas. You don't want to cut them too short, because then you don't have room to build your fillet. We're laying this out on the table again. We're locating exactly where all the tubes should be, and we're going to get everything clamped into place. All right, we're putting we're tacking the top tube in place now. 4 tacks should do it. You notice I don't have my heat sink in the head tube at this point. We don't need the heat sink in there just for a tack. Once we get the tack in there, we'll put the heat sink back in. We don't want to do that joint without the heat sink in place. This is a really thin area right here where we're putting this tack. That's about the thinnest area that you're going to work on the whole bike. So we have to work quickly there. We have to keep our flame kind of flat and feather that flame rather than point it, or brush the flame rather than point it at the tube. There, we've got 4 tacks there. All right, here we are. We're doing the final brazing. Notice that the heat sink is in the head tube there, hanging down below, but it has been inserted all the way, and it's what keeps the head tube from becoming ovalized, and also it keeps the head tube straight. If the heat sink were not in there, the head tube would curve around and it would be rounded on the front. Right now we're building webs. We just built a web on the top there, and now we're going to build a web on the underside. You'll end up building kind of a big web in this area between the down tube and the top tube. You'll spend a little bit of time on that. You'll notice all throughout this that I continually tilt the frame a lot. Several times a minute the frame gets tilted. Notice how the frame is being held flat now. And we're using that web that we built between the down tube and the top tube as a dam to fill in that area. You're basically doing about 3 different jobs here during this brazing. Initially, you're building up an area, and that of course takes lots of brass, and you have to do the dabbing, the constant dabbing, and you have to use the higher heat. Then after that, you do what I call sculpting, and you add your brass and you kind of float it out, and you use the gravity to try to manipulate where that brass is going to be. And then finally you do a final cleanup, and you go over the joint and you smooth out a lot of the little bumps. It takes many frames to get used to doing all this all at once. We're kind of finishing things up here. When we finish this up, we'll have to let the frame cool sufficiently so that we can put it in the soak tank to soak off all the flux. And then after it soaks cool, we'll be able to get the plugs out of the head tube and out of the seat tube. After the frame has had sufficient time to cool, then you can soak the flux off in hot water. Of course, will take it off faster than cold water. When the flux has been removed, then the cleanup can start on the joints. And the first thing I like to do is go over these areas with a file. Usually a 6-inch or an 8-inch Nicholson half-round file does the trick, the curved surface of the file. Sometimes I change to a 10-inch round file. After you've gone over all the joints with the file, if you're lucky enough to have one of these, you can use a Dynafile made by the Dynabraid company. This particular one is an electric one. They're kind of hard to get these days, but the pneumatic ones are still available, and they still have all the same style tips that are available with them. You have to be very careful with this tool. It's a real metal eater. It does a beautiful job cleaning up, but it will also do a really fast job of undercutting. Undercutting is a very undesirable effect where you leave the brass area and you go on to the steel, and when you hit the steel, you cut below the surface of the steel, so that when the bike is painted, you see these grooves where the fillet ends and the steel starts. It looks very, very unsightly, and it takes a while before a frame builder doesn't do this undercutting. There are some brands of these hand-operated belt sanders that are available for considerably less than the Dynafile. The Dynafile is probably the most expensive one on the market, but there are some that you can get at some of your standard auto supply stores that come in for under $100. You could keep an eye open for one of those. At any rate, this takes, this is some meticulous work, some careful work. You have to be careful with that tool, or you'll do some nasty things to your joints. This tool has an incredible ability to get into some really tight areas that you never thought you'd be able to get into with a power tool. We aren't doing the bottom bracket shell yet, because the bottom bracket shell still has the chainstays to put in place. We're not doing the seat cluster because the seat stays still have to be put in place. So we're just going to concentrate on the head tube right now. The final step with the head tube is to do a final sanding with the 1-inch wide emery cloth strips. I like to do it underneath my thumb. Kind of wears out your thumbprint after a while, but it gives you very good control over your sanding. This takes quite a while, but it really does finish out the joint quite nicely.